The universe's most precise clocks have a hidden wobble. Deep in space, spinning stellar corpses called pulsars keep near perfect time, yet they possess a subtle, rhythmic sway known as precession. This tiny imperfection, born from a fundamental asymmetry in the star itself, is not a flaw but a feature. By the end of this exploration, you will understand how this cosmic wobble unlocks the secrets of matter denser than an atomic nucleus. We will uncover how a star's lopsided shape can act as a probe into its mysterious interior, and how this knowledge might one day power a galactic positioning system. What invisible threads connect a star's slight imbalance to the future of physics itself? This rhythmic pulse is the heartbeat of a cosmic corpse. To grasp the wobble, we must first meet the star itself. We call it a pulsar, but its true nature is even more extreme. A pulsar is a neutron star, the collapsed core of a giant star that exhausted its fuel and exploded in a supernova. That colossal death squeeze crushes an object with more mass than our Sun down into a sphere only about the size of a city. The result is matter so dense it defies comprehension. Picture a single teaspoon full of this material. That tiny amount would not weigh a few grams or even a few kilograms. It would weigh billions of tons, as much as a mountain here on Earth. This incredible density is paired with a dizzying spin. A newborn pulsar can rotate hundreds of times every single second. Now, imagine this impossibly dense, rapidly spinning object in the void of space. It possesses a powerful magnetic field, and from its magnetic poles, it fires out intense beams of radiation, much like a lighthouse projects a rotating beam of light. The pulsar spins, and those beams sweep through the cosmos. Our detection of a pulsar is simply a matter of perspective. If our planet happens to lie in the path of one of those sweeping beams, we observe a regular, repeating pulse of energy with every rotation. That steady, metronomic blink is the signature of a cosmic lighthouse, and it is this very precision that makes its subtle wobble so profoundly important. That steady cosmic pulse, the heartbeat of a dead star, is not always perfectly metronomic. Sometimes there is a wobble. This wobble has a name, and it is a phenomenon you have likely seen with your own eyes. Think of a child's spinning top. When it is new and perfectly balanced, it spins on its axis with a beautiful, upright stability. But if that top becomes slightly lopsided, perhaps from a small chip or an imperfection, its behavior changes dramatically. It no longer spins perfectly upright. Instead, the entire axis of its spin begins to slowly trace a circle in the air. The top itself wobbles, and this slow, graceful circling of its spin axis is known as precession. The same principle governs a gyroscope, where the slow, persistent rotation of its base makes the spinning wheel itself seem to defy gravity, its axis slowly moving in a lazy circle. Precession is the universal dance of any spinning object that is not perfectly symmetrical. Now, shift that scale from a toy on a table to a city-sized star spinning in the void. A pulsar is a colossal gyroscope, a spinning sphere of ultra-dense matter. If this star possesses even a tiny asymmetry, a slight bulge or a minuscule mountain on its otherwise smooth surface, the relentless laws of physics demand a response. That imperfection, that cosmic imbalance, forces the star's spin axis to wobble. Just like the lopsided top, the pulsar begins to precess. Its north and south poles slowly trace a circle in space over vast periods of time. This means the beams of radiation shooting from its magnetic poles, our guiding lighthouse beams, do not sweep through the same exact path forever. Their path slowly, subtly changes. This is the secret behind the rhythmic sway in the pulsar's signal, a tiny tremor in the most precise clocks in the universe, born from a star that is not quite round. This wobble is a direct message from the star's deepest structure. Why would a cosmic gyroscope, a sphere of such immense density, begin to sway? The universe provides a single, elegant answer. Asymmetry, a perfectly symmetrical sphere spinning in the void, would maintain a perfectly stable spin axis forever. It would be the ultimate timekeeper, its pulse as unerring as a mathematical constant. But nature rarely deals in perfect geometries. Pulsars are not perfect. They are the scarred remnants of stellar catastrophes, and they carry the marks of their violent origins. This tiny imperfection, this cosmic imbalance, is the very engine of precession. So what could possibly make a star lopsided? The possibilities are as fascinating as they are varied. Picture a mountain on the surface of this neutron star, but this is no ordinary mountain. Compressed by gravity beyond belief, this feature might be only a few centimeters high, yet it would contain the mass of an entire terrestrial mountain range. That tiny lump of excess mass, offset from the star's axis of rotation, would be enough to make the entire colossal object wobble as it spins. Another possibility is frozen into the star's very shape. Its formation in the supernova explosion was an event of unimaginable chaos. The collapsing star may have solidified into a shape that is not quite a sphere, but a slightly squashed or elongated ellipsoid, its asymmetry locked in place by its own incredible density. Or perhaps the most profound source of wobble lies deep within, hidden from view. A neutron star is not a uniform ball. It is thought to have a rigid outer crust, a crystalline shell kilometers thick, floating atop a bizarre inner sea. This interior is a superfluid, a state of matter that flows without any friction whatsoever. If this slippery, rotating core becomes even slightly misaligned with the solid crust spinning above it, a delicate and complex tug of war begins. The two components, locked in a gravitational embrace, try to pull each other into alignment. This internal struggle between the star's different layers can itself manifest as a slow, persistent wobble in its overall spin. That tiny tremor in the pulsar's rhythm is therefore a coded signal. It tells us that the star is not a perfect sphere, that it has a mountain, or that its heart spins at a different pace than its skin. This minuscule flaw becomes our most powerful tool for seeing the unseeable. Detecting this cosmic wobble requires listening with unimaginable precision. We are tracking an object that might be thousands of light years away, a tiny speck spinning in the void, and we are trying to measure a sway in its axis so slight it will be imperceptible to the naked eye across the entire solar system. Our only connection to this distant gyroscope is the rhythmic pulse of its lighthouse beam. As the pulsar precesses, its spin axis slowly circles, and this gradual shift changes the path of its radiation beams through space. Think of a lighthouse on a stormy coast. If the entire lighthouse structure were to slowly tilt, even by a fraction of a degree, the sweeping beam of light would hit the shore at a slightly different time and from a slightly different angle each night. The keeper in the watchtower would note that the flash is arriving a moment early one week and a moment late the next. This is exactly how we read the wobble from across the galaxy. The precession alters when the pulsar's beam sweeps across our line of sight. 1 month, the beam might point directly at us a tiny bit sooner than our models predict. Months or years later, it might arrive a fraction of a millisecond late. These are not random errors. They form a predictable, repeating pattern over time, a slow oscillation in the timing of the pulses that reveals the stately, slow-motion dance of the star's spin axis. But astronomers go even further. The changing orientation can also affect the shape of the pulse we see. The beam is not a perfectly sharp pencil line of radiation. It has a width and a structure. As precession changes our viewing angle into this beam, we might detect a slight widening of the pulse or a change in its brightness, as if we are seeing the lighthouse beam from its edge rather than its center. To piece this story together, scientists collect data points not for days or weeks, but for years and often for decades. They build up a timeline of millions upon millions of individual pulses, searching for that consistent, rhythmic drift hidden within the near-perfect ticking. It is a testament to human patience and ingenuity, a decades-long vigil to decode the faint whisper of a wobble from a stellar corpse, transforming it from a ghost in the data into a precise measurement of cosmic motion. That faint rhythmic sway is a direct line into the star's hidden heart. This is where a simple wobble transforms into a revolutionary tool, a form of cosmic echolocation that lets us map the impossible. We cannot drill into a neutron star, nor can we recreate its interior in any laboratory. Its core is a place where matter is squeezed into forms that defy our everyday understanding of physics. Yet the precession gives us a window. The way a pulsar wobbles, the precise speed and pattern of its gyroscopic dance, is exquisitely sensitive to what is happening inside. It all comes down to how mass is distributed. A perfectly uniform, rigid sphere would precess in one specific way, but a neutron star is a complex, layered object. Its outer layer is a rigid crust, a crystalline lattice of atomic nuclei so dense it is harder than diamond. Beneath this shell, physicists believe there exists a quantum ocean, a superfluid of neutrons. This superfluid has no viscosity. It flows without any friction at all, a state of matter we can only create in tiny samples for fleeting moments in labs on Earth. Inside the pulsar, this superfluid might be rotating at a slightly different speed than the solid crust above it. This internal mismatch creates a subtle gravitational tug, a dynamic imbalance that directly influences the star's overall wobble. The precession becomes a conversation between the crust and the core. By measuring the wobble with extreme precision, we can start to ask profound questions. How thick is the solid crust? How much of the star's mass is locked in this frictionless superfluid? Is the core a soup of free quarks, or does it form exotic states like nuclear pasta, a bizarre material with the density of an atomic nucleus but structures that resemble lasagna or spaghetti? Each of these possibilities would leave a unique fingerprint on the precession. A star with a thicker, more rigid crust would wobble differently than one with a thinner, more elastic shell. A large, misaligned superfluid core would imprint a specific rhythmic signature onto the timing of the pulses. It is like listening to the sound a glass makes when you tap it. A trained ear can hear if the glass is full or empty, or if it has a hidden crack. In the same way, by listening to the precise sound of a pulsar's wobble across years and decades, we are learning to hear the structure of its interior. We are performing a remote magnetic resonance imaging scan on an object thousands of light years away, decoding the architecture of matter itself from the gentle sway of a spinning corpse. The Vela pulsar brings this entire cosmic theory down to Earth. Discovered in the late 1960s, it sits roughly 1,000 light-years away, the spinning heart of a supernova that exploded millennia ago. It blinks with remarkable speed, rotating about 11 times every single second, and for decades, radio telescopes have meticulously recorded its rhythmic beat. At first, its pulse seemed perfectly predictable, a metronomic flash in the dark. But over years of patient observation, a subtle story began to emerge in the data. The shape of its pulse, the specific pattern of its radio wave signal, was not staying constant. It was slowly, steadily changing. The pulse profile was evolving, as if the lighthouse beam itself was gradually widening and then narrowing again over a cycle spanning approximately 120 days. This was not a random fluctuation. This was a repeating pattern, a long-term modulation that pointed to one inescapable physical cause. The entire star was wobbling. Its spin axis was precessing, completing one full slow circle every 120 days. This meant our view into its lighthouse beam was constantly shifting. One month, we might be looking directly down the center of the beam, receiving a strong, sharp pulse. Months later, as precession carried the beam's orientation, we might be viewing it more from the edge, resulting in a wider, more diffuse pulse profile. This real-world observation transformed abstract theory into confirmed fact. The Vela pulsar's precession became a direct, observable key, allowing scientists to begin calculating the star's internal structure to estimate the rigidity of its crust and the nature of its superfluid core from that 120-day wobble. This gentle wobble does more than just reshape a beam of light. It sends ripples through the fabric of space and time itself. The connection lies in one of Einstein's most stunning predictions: gravitational waves. Any massive object that accelerates creates these ripples, but for us to detect them, the acceleration must be immense, involving objects of incredible density. A spinning neutron star is a perfect engine for gravitational waves, especially if it is not perfectly round. Its asymmetry means that as it spins, it is constantly redistributing its mass in a non-uniform way, effectively stirring the spacetime around it. Now add precession into this mix. A precessing pulsar is not just spinning, its entire axis of rotation is slowly circling. This complex, compounded motion creates a far richer and more intricate pattern of gravitational radiation than a simple, steady spin ever could. It is the difference between a single, pure note played on a violin and a complex, evolving chord. This intricate signal carries within it a detailed fingerprint of the star's asymmetry, its exact shape, and the dynamics of its interior. But there is a catch. The gravitational waves from a lone, precessing pulsar are incredibly faint, lost in the background hum of the cosmos. To amplify the signal, nature provides a perfect partner. Place that wobbling pulsar in a binary system orbiting another dense star. Now you have a celestial dance of almost unimaginable precision, with the pulsar both wobbling on its axis and swinging around a companion. This dual motion imprints a highly specific, oscillating signature onto the gravitational waves it emits. For our current ground-based observatories, this signal remains just out of reach, a whisper too quiet to hear over the din of the universe. But the future of listening is already being built. Imagine a gravitational wave observatory not on the Earth's surface, but in the pristine quiet of space. The Laser Interferometer Space Antenna, or LISA, is precisely that, a mission being designed to open a new low-frequency window onto the cosmos. With 3 spacecraft flying in a vast triangular formation millions of kilometers apart, LISA will be exquisitely tuned to hear the low, rumbling hum of systems like binary pulsars. It is an instrument designed to listen for the specific, complex chords played by a wobbling, orbiting pulsar. By detecting these intricate gravitational ripples, we gain an entirely new, independent way to probe the star's heart. The precession we once measured only through its shifting radio beams will now be confirmed by the warping of spacetime itself. This independent measurement is the key to breaking open the mystery. It allows scientists to cross-check their models of the neutron star interior, testing whether the structure deduced from the radio wobble matches the structure implied by the gravitational wave signal. Any discrepancy would be a revolution, a sign that our understanding of matter under such extreme pressure, or even our grasp of gravity itself, requires a fundamental rewrite. The faint wobble of a distant star, once a mere curiosity in the timing of pulses, becomes a direct line into the most profound questions of physics, its message carried not just by light, but by the very stretching and squeezing of the universe. That faint wobble, once a complication, becomes the very key to navigating the galaxy. The incredible regularity of a pulsar's pulse makes it a potential cosmic lighthouse, a fixed point in the dark. An entire network of these celestial clocks could form the backbone of a navigation system far surpassing anything we have today. This is the vision of a pulsar timing array. Picture a future spacecraft voyaging between the planets or even to the stars. Instead of relying on signals from satellites orbiting Earth, its onboard computer listens to the rhythmic ticks from multiple pulsars in different directions across the galaxy. Each pulsar is a unique beacon with its own distinct pulse frequency, like a radio station with its own call sign. By measuring the precise arrival time of pulses from at least 4 different pulsars, The spacecraft can triangulate its position in three-dimensional space with astonishing accuracy, just as your phone uses signals from multiple GPS satellites. But there is a catch. Precession introduces a slow, predictable drift in the timing of those pulses. If our navigation system treated the pulsar as a perfect metronome, it would slowly accumulate errors. The spacecraft would believe it was in one position, while in reality, it could be hundreds of kilometers off course. This is not a flaw in the system. It is a feature we must account for. To build a reliable galactic positioning system, we must first become masters of the wobble. We need to observe these pulsars for years, even decades, to precisely map their individual precession cycles, their unique rhythmic sway. We must create a detailed model for each one, a celestial almanac that predicts not just its pulse, but its pulse's slow, graceful evolution over centuries. Once we have that deep understanding, we can program our navigation computers to automatically correct for the precession. The system would know that Pulsar Vella's pulse is currently arriving a few microseconds early in its 120-day wobble cycle, and it would adjust its calculations accordingly. This transforms the wobble from a source of error into a built-in correction, a testament to our profound understanding of these distant stars. The result is an autonomous navigation system of unparalleled precision, a network of cosmic clocks whose every imperfection is known and compensated for, guiding our ships with confidence through the silent ocean between worlds. Beyond the star's mass and shape lies another colossal force sculpting its wobble. An invisible architecture of power wraps around the pulsar, a magnetic field so strong it could strip the data from every credit card on Earth from 500,000 miles away. This field is not a perfect halo centered on the star. It is anchored at the magnetic poles, and for most pulsars, these poles are not aligned with the axis of spin. Picture a simple bar magnet. If you spin it around its center, it is symmetrical. But if you spin it around a point off to one side, the entire system becomes lopsided. The magnetic field itself becomes a source of asymmetry. This misalignment means the star's immense magnetic energy is not distributed evenly. One side of the spinning object carries a slightly different electromagnetic weight than the other. This creates a subtle but persistent torque, a force that can nudge the spin axis, initiating or sustaining the slow, gyroscopic wobble of precession. Now take this concept to its most extreme conclusion. Meet the magnetar, a neutron star with a magnetic field 1,000 times more powerful than that of a typical pulsar. These are the supermagnets of the cosmos, with fields so intense they can twist the star's iron crust, causing catastrophic starquakes. These quakes release more energy in a fraction of a second than our sun will emit in 100,000 years. In such an environment, the role of the magnetic field is not just a contributor to precession, it can be the dominant force. The magnetic pressures on a magnetar are so unimaginably vast that they can literally warp the star's solid crust, creating deformations and mountains that make it profoundly lopsided. This magnetic sculpting could drive a far more violent and dramatic precession than we see in common pulsars. Some theories even suggest that the sudden, enormous energy release of a starquake could abruptly change the star's rotation or its internal structure, giving its precession a sudden jolt, a cosmic shudder that would be written into the timing of its pulses for years to come. The wobble of a magnetar is not a gentle sway. It is the tremor of a star under siege by its own unimaginable power, a direct signal from the most magnetic objects in the known universe. These sudden jumps in a pulsar's spin are known as glitches, and they might be the cosmic equivalent of a shudder running through the star. For decades, these tiny speed-ups were a perplexing mystery. A pulsar that had been steadily slowing down for years would, without warning, suddenly spin a fraction of a percent faster, as if something inside it had given way. The prevailing theory points to the star's interior, to the frictionless superfluid sea of neutrons. Think of the solid crust as a bowl filled with a bizarre, spinning liquid. The crust slows down gradually over time, but the superfluid inside, with no friction to hold it back, can keep spinning at its original, faster rate. It becomes pinned to the crust, storing immense rotational energy. Then something gives. Perhaps the crust cracks under the strain, or the superfluid vortices suddenly unpin themselves. In an instant, a colossal amount of that stored momentum is transferred from the superfluid core to the solid crust, kicking the star's rotation to a slightly faster speed. This is the glitch. Now, consider what this violent internal rearrangement does to the star's shape. That sudden transfer of momentum and energy is not a gentle process. It is a stellar-scale earthquake. Such an event could easily create a new mountain on the surface, a tiny lump of concentrated mass, or it could alter the delicate balance between the crust and the core, changing the star's internal asymmetry. And any change in the star's asymmetry directly changes its precession. The wobble itself could be kicked, nudged, or reset by the glitch. This is the cutting-edge connection scientists are now exploring. Could a glitch be the trigger that starts a precession, or the event that suddenly stops one? Could the subtle changes in the wobble pattern after a glitch reveal exactly what broke inside the star and where? Observing a pulsar that both glitches and precesses would be like having a window into its seismic life. The glitch tells us the star's interior has violently rearranged itself, and the subsequent changes to its wobble tell us precisely how that rearrangement altered its fundamental shape. Two separate mysteries, the sudden jump and the slow sway, begin to weave together into a single dynamic story of a living, changing stellar remnant. These wobbling stars are nature's ultimate physics laboratories. Pulsars provide a pristine environment to test the fundamental laws of the universe, particularly Einstein's theory of general relativity. This theory describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. Its predictions are exquisitely subtle, often lost in the complex noise of most celestial systems. But a pulsar is different. Its rotating beam acts as a near-perfect clock, allowing us to track its motion through the gravitational landscape with mind-bending precision. When a pulsar orbits another dense object, the two bodies create a warp in space-time, and the precise timing of the pulses allows us to map that warp. We can measure how the orbit slowly decays as energy is carried away by gravitational waves, exactly as Einstein predicted. We can see how the pulsar's signal is delayed when it passes behind its companion, its light struggling against the gravity well. Each pulse is a data point in a decades-long experiment, confirming the details of general relativity with a confidence that is difficult to achieve anywhere else. But this entire framework relies on knowing exactly where the pulsar is pointing at any given moment. That is where precession becomes absolutely critical. If we ignore the star's wobble, if we model it as a simple, stable spinner, we introduce a subtle, slow error into our timing measurements. Our map of the pulsar's orbit becomes smeared. We might mistake the slow, rhythmic change caused by precession for an anomaly in the orbit itself, or even misinterpret it as evidence for a new gravitational effect. To use these cosmic clocks for their most precise work, we must first subtract the wobble. We must build a model that accounts for the slow, graceful precession of its spin axis. Only then can we see the true, clean signal of pure gravity. This refinement makes our tests of general relativity far more stringent. We are no longer just testing gravity, we are testing it with a clock that we understand down to its most subtle imperfections. Any tiny discrepancy that remains after we have accounted for every known factor, including precession, becomes profoundly significant. If the observed wobble of a pulsar does not perfectly match the prediction from general relativity, it could mean that our understanding of gravity is incomplete. Perhaps matter behaves differently under such extreme densities, warping spacetime in a way Einstein's equations do not anticipate. Or perhaps gravity itself operates with slight modifications on these immense scales. A single, well-measured precession that defies prediction could be the thread that unravels our current model of the universe, pointing the way to a deeper, more complete theory of reality itself. The initial lopsidedness of a pulsar is forged in the fire of its own violent birth. A supernova explosion is not a polite, spherical blast. It is a chaotic, directional event, a stellar detonation so powerful it can literally kick the newborn neutron star out of its own stellar nursery. This cosmic recoil propels the star across the galaxy at speeds reaching hundreds of kilometers per second. The crucial detail is that this kick is almost never delivered straight on. The immense forces at play during the core collapse are fundamentally messy and uneven. Vast jets of neutrinos and material might erupt more strongly from one side than the other, or the explosion itself might be lopsided, a colossal imbalance in the final moments of the star's death. This asymmetric kick does more than just send the star flying. It imparts a tremendous, one-sided force on the newborn neutron star while its outer layers are still cooling and solidifying. Picture a potter slamming a fist into one side of a spinning lump of wet clay. The entire form jerks and deforms, its symmetry shattered in an instant. In the same way, that violent, off-center kick can permanently warp the pulsar, creating the very deformations that seed its future wobble. A mountain might be forged in that single traumatic moment, or the entire star might be frozen into a slightly squashed shape as it solidifies under extreme pressure. This means the precession we observe millennia later, the slow, rhythmic sway in its lighthouse beam, is not a later development. It is an echo of that first explosive shove, a memory of its violent entry into the universe, written into its spin and playing out across the eons. This wobble is a direct probe into the physics of the impossible. Every measurement of a pulsar's precession, every subtle shift in its rhythmic sway, is a vote for or against a specific equation of state. This term sounds abstract, but it represents the single most important question about a neutron star. The equation of state is the fundamental rulebook that dictates how matter behaves when crushed to densities beyond an atomic nucleus. It describes the precise relationship between the immense pressure pushing inward at the star's core and the resulting density of the material there. Is the core stiff, resisting further compression so fiercely that the star remains large and relatively fluffy by neutron star standards, or is it soft, yielding easily to gravity, allowing the star to collapse into a much smaller, even denser object? Each possibility, each different equation of state predicts a different internal structure. A stiff star would have a thick, solid crust. A soft star would have a thin, brittle shell over a vast liquid interior. And these internal architectures wobble in distinctly different ways. A star with a thick, rigid crust will precess at one rate, while a star with a more fluid interior will precess at another. By meticulously measuring the precession of real pulsars, we are effectively conducting a remote audit of their internal pressure and density. We are collecting data that tells us which equations of state are possible in our universe and which are mere mathematical fantasies. This is not just an academic exercise. The knowledge of how matter behaves under such extreme confinement could one day revolutionize our own technology. We are learning the rules for creating materials of incredible density and strength in a realm governed by quantum forces we are only beginning to understand. The principles locked inside a pulsar's heart might one day inform the design of entirely new forms of matter here on Earth, materials with properties we can currently only dream of, pushing the entire field of material science into a new frontier. The wobble of a pulsar tells its story in more than one language. This single cosmic phenomenon speaks through the rhythmic flashes of radio waves we have patiently recorded for decades, and it promises to whisper through the ripples in spacetime that future observatories will detect. It even theorizes a third, more elusive language, that of neutrinos, ghostly particles that could stream directly from the star's superheated heart during a violent rearrangement. Each of these messengers brings a unique piece of the puzzle. The radio pulses map the external consequence of the wobble, the changing sweep of the lighthouse beam. Gravitational waves will probe the internal dynamics, the bulk motion of mass that generates the wobble itself. And neutrinos, should we ever detect them from such an event, would offer a fleeting snapshot of the energy released deep within the core, perhaps during a starquake that altered the precession. This collaborative approach is the essence of multi-messenger astronomy. It is the difference between trying to understand a complex machine by only looking at its spinning dials and being able to also listen to its internal hum and feel the heat from its engine. By combining the radio view, the gravity view, and someday the particle view, we are not just adding data points. We are building a complete, multi-dimensional portrait of this spinning stellar corpse. We see its surface, feel its gravity, and sense its inner fire all at once. This holistic method, where every type of cosmic signal is woven together into a single narrative, is how we will finally read the full story written in a pulsar's sway, transforming our fragmented glimpses into a profound and unified understanding of the universe's most extreme matter. Decoding this cosmic wobble is a monumental task of patience and precision. The signals we are chasing are astonishingly weak, a whisper of a whisper buried in decades of data. Imagine trying to hear the slow, deep note of a cello being played 1,000 miles away while standing in the middle of a roaring hurricane. That is the scale of the challenge. The precession of a pulsar reveals itself not in days or weeks, but over years and often decades of relentless observation. Scientists must collect millions, even billions, of individual pulses, building a timeline so vast that the subtle, rhythmic drift of the wobble finally emerges from the random noise of the cosmos. This is not a project for a single PhD student or a single research grant. It is a legacy of effort, a scientific baton passed from one generation of astronomers to the next. Then comes the Herculean task of interpretation. The models that attempt to describe this wobble are mathematical nightmares of breathtaking complexity. You are not just modeling a spinning sphere, you are trying to simulate a lopsided, magnetized, superfluid-filled gyroscope where a crust of iron harder than diamond floats atop a frictionless quantum ocean, all while the entire object moves through the warped spacetime of its own gravity. Every single component, from the magnetic field's torque to the vortices in the superfluid, influences the wobble in a delicate, interconnected dance. Untangling this web requires some of the most powerful supercomputers on Earth, running simulations for months to see if their virtual pulsar wobbles in the same way as the real one thousands of light years away. Our ability to even attempt this work rests on the shoulders of giant telescopes. For decades, the legendary Arecibo Observatory in Puerto Rico provided a treasure trove of data on countless pulsars, its massive dish gathering radio waves with unmatched sensitivity. Its legacy data sets, archived and revisited again and again, continue to fuel new discoveries about precession long after the telescope itself is gone. And the future is even brighter. The upcoming Square Kilometre Array, or SKA, promises to revolutionize this field. This is not a single telescope, but a vast network of thousands of antennas spread across 2 continents. When complete, the SKA will be so sensitive it could detect a radar transmitter on a planet orbiting a nearby star. For pulsar astronomers, it will be like switching from a modest hearing aid to the most advanced ears in the universe. The SKA will monitor thousands of pulsars simultaneously, with a precision that will allow us to detect wobbles far fainter and more subtle than any we have seen before. It will provide the rich, pristine data needed to finally test our most complex models, to hear the true music of these spinning stellar corpses, and to read the detailed story of their hidden hearts. This gentle wobble is a universal signature written across the cosmos. Pulsars are not the only celestial bodies that trace these slow, graceful circles. Our own solar system holds a classic example in the planet Mercury. Its orbit around the Sun is not a static, repeating ellipse. Instead, the entire elliptical path itself slowly rotates, a phenomenon known as the precession of its perihelion. This is not a wobble of the planet's spin, but a precession of its entire orbital path, a subtle effect that was one of the first key confirmations of Einstein's theory of general relativity. Closer to home, our Earth itself is a giant precessing gyroscope. The planet's axis slowly traces a circle in the sky over a cycle of about 26,000 years. This is why the star Polaris will not always be our North Star. In a few thousand years, the Earth's axis will point toward a different star, Vega, as this grand celestial precession continues its stately march. Even the most extreme objects in the universe obey this rule. Spinning black holes, the gravitational monsters born from collapsed stars, can also precess. Their intense gravity warps the space around them so severely that the orbits of nearby matter and even the spin axis of the black hole itself can undergo a complex relativistic wobble. So precession is a fundamental physical process, a dance of spinning masses that plays out from the scale of a child's top to the realm of galactic cores. What makes pulsars so special is not that they wobble, but what their specific wobble can tell us. While Mercury's precession tests gravity itself, and Earth's precession marks the slow turning of the ages, a pulsar's precession is a direct probe into a state of matter that cannot be created or studied anywhere else. It is the only window we have into the heart of an atomic nucleus scaled up to the size of a city, a unique and precious key to the physics of the impossible. The hunt for these cosmic wobbles is about to leap into a new era of discovery. We stand at the precipice of a revolution, driven by technologies that will transform our subtle observations into crystal-clear revelations. The sheer volume of data from next-generation telescopes is so immense that no human team could ever sift through it all. This is where artificial intelligence takes its place as an essential partner. Machine learning algorithms trained to recognize the faintest rhythmic patterns will scour decades of pulse timing data, uncovering wobbles so slight they have remained hidden until now. These AI systems will not replace scientists, but will act as tireless assistants, flagging the most promising signals in a cosmic haystack for human minds to interpret. Our view will also expand beyond the radio spectrum. Space-based X-ray telescopes operating far above our atmosphere's distortions will offer a completely different perspective. Many pulsars beam their most energetic radiation in X-rays, and observing their precession in this high-energy light could reveal details about the searing hotspots at their magnetic poles, details that radio waves simply cannot show. It is like examining the same lighthouse with night vision goggles instead of the naked eye, revealing a hidden layer of its structure and activity. But the ultimate confirmation may arrive not as light but as a ripple. The long-held dream is to detect the continuous, low hum of gravitational waves emitted directly by a lone, precessing pulsar. This signal would be the purest expression of its wobble, a direct tremor in spacetime caused by its asymmetric spin. Catching this faint, persistent whisper would open a gravitational window straight into the star's heart, allowing us to weigh its deformities and measure the rigidity of its interior with a ruler made from the fabric of the cosmos itself. We are no longer just listening to the ticks of these cosmic clocks, we are preparing to feel their vibration in the universe itself. The ultimate goal of reading this wobble is to rewrite the textbooks of fundamental physics. Deep within the pulsar's core, the rules are governed by a theory known as quantum chromodynamics, the complex science of the strong nuclear force that holds atomic nuclei together. This is the domain of quarks and gluons, the universe's most basic building blocks. On Earth, we can only study this force in fleeting, high-energy collisions or within the confines of a single atom. But inside a neutron star, quantum chromodynamics is not a fleeting event. It is the permanent, crushing reality. The immense pressure and density there force quarks into behaviors and arrangements we can only theorize about. One profound possibility is that the neutrons themselves break down, their identities dissolving into a seething, primordial soup known as quark matter. This state, a quark-gluon plasma, is thought to have existed just microseconds after the Big Bang. Another, even more exotic idea is color superconductivity, where quark pairs flow with zero resistance in a perfect, frictionless current that makes our best earthly superconductors seem crude by comparison. These are not just abstract concepts, they are potential phases of matter, and each one would give the neutron star a different internal structure, a different squishiness or stiffness. This is where the wobble becomes our only possible experiment. The precise way the pulsar precesses depends entirely on this internal stiffness, on the equation of state dictated by quantum chromodynamics under these impossible conditions. If the precession data from a real pulsar matches the prediction for a star with a quark matter core, it would be the first direct evidence that such a phase of matter can exist in a stable form. It would confirm a theoretical pillar of modern physics in an environment no lab could ever create. Every subtle sway of the star's axis is a vote for one version of this quantum reality over another, a direct message from a realm where matter itself is fundamentally transformed. You do not need a billion-dollar telescope to join this cosmic hunt. The rhythmic pulse data from these distant stars is not locked away in a private vault. Vast archives of pulsar timing information are publicly available, a digital treasure trove waiting for curious minds to explore. This is where the search for the wobble becomes a global, collaborative effort, one you can join from your own home. Citizen science projects have opened the doors of astrophysics to everyone. Platforms like Einstein at Home invite the public to download a small program that runs in the background of a personal computer or smartphone. While you sleep or work, your device sifts through the same mountains of data that professional astronomers use. It analyzes the arrival times of millions of pulsar pulses, searching for the tiny, systematic drifts that betray a precession. You are not just playing a game, you are processing genuine scientific data. The algorithms are looking for patterns too subtle for the human eye to easily spot in such a massive dataset, the faint rhythmic signature of a wobble hidden within years of observations. This process truly democratizes discovery. A student, a teacher, or an artist with a laptop can be the first to flag a promising signal in a pulsar's timing, a signal that might lead to a confirmed wobble and a new window into that star's interior. You are analyzing the same data, using the same computational tools, and contributing to the same grand scientific endeavor as the researchers at the world's great observatories. Every processed data set brings us one collective step closer to mapping the heart of a neutron star, turning the solitary work of cosmic observation into a shared human achievement. The next great clue in understanding the universe's most extreme matter could be uncovered by your computer, a quiet participant in the greatest detective story ever told. Science fiction has often reached for the stars, but how accurately has it grasped these cosmic lighthouses? The iconic starship Enterprise from Star Trek famously used pulsars as navigational markers, treating their steady pulses as fixed points on a galactic map. This idea is not pure fantasy. It is a direct and surprisingly prescient mirror of the pulsar timing arrays scientists are developing today. The writers envisioned a future where the natural rhythms of the cosmos guide our voyages, a concept grounded in real physics. Yet fiction often takes a creative leap into the impossible. Some stories have imagined pulsars as weapons, their beams harnessed to destroy planets or as gateways to other dimensions. The scientific reality is both more subtle and more profound. A real pulsar's beam is a focused stream of radiation, not a destructive laser capable of obliterating worlds. Its power lies in its clock-like precision, not in raw, explosive force. And while its intense gravity warps space, it does not rip open holes in the fabric of reality. These fictional exaggerations, while entertaining, highlight a deeper truth. They represent our innate desire to personify the cosmos, to turn distant, incomprehensible objects into active characters in a galactic story. By contrasting the myth with the reality, we demystify the pulsar without robbing it of its wonder. We replace the fantasy of a planet-destroying weapon with the genuine marvel of a city-sized object that can help us test the laws of physics themselves. This bridge between science fiction and science fact does not diminish the stars. Instead, it grounds our awe in a foundation of understanding, showing that the true story of a wobbling pulsar is more compelling than any fiction. Visualizing the slow, graceful wobble of a pulsar requires a leap of scale and time. Picture a three-dimensional model of the star floating in darkness, its surface a tapestry of magnetic fields and intense heat. Two brilliant beams of radiation lance out from its magnetic poles, sweeping through the void like cosmic searchlights. Now set the entire star in motion, spinning at a dizzying rate. But then introduce the precession. The entire spin axis, the invisible rod running through the star's core, begins a slow, majestic circle. The beams no longer carve out the same perfect cone in space, their path shifting imperceptibly with each rotation. A timeline below the star compresses years into seconds, graphing the shape of the pulse we receive. As the precession carries the beams, our viewing angle changes. The pulse profile on the graph widens and softens, then sharpens and intensifies in a slow, rhythmic dance, a direct visual correlation between the wobble in space and the data on our screens. To understand why it wobbles, we must see the star's hidden asymmetry. The smooth sphere could fracture, revealing a lopsided interior. Perhaps one hemisphere of the crust is slightly thicker, a vast, dense region colored in deep crimson to show its greater mass. Or a single, impossible mountain rises from the surface, a microscopic bump containing the mass of an entire planet, throwing the star's balance off in a profound way. The most telling visualization might split the star in half. The outer crust, a crystalline shell, rotates as a solid piece, but inside we see a swirling, ethereal superfluid, a quantum ocean of neutrons represented by flowing, iridescent currents. This inner sea spins on its own axis, slightly misaligned with the crust. We can see the gravitational tug of war between them, the invisible forces stretching and pulling, a dynamic struggle that manifests as the steady, observable wobble of the entire star. These are not just pretty pictures, they are the key to translating a complex physical reality into a story our minds can grasp and remember. This cosmic wobble forces us to confront a profound duality in nature itself. We often search the heavens for perfect order, for immutable laws and flawless celestial clocks, yet here is a phenomenon born from a fundamental flaw. The pulsar's precession is a perfect imperfection, a tiny crack in an otherwise unbreachable facade of regularity. It whispers that chaos and order are not opposing forces but partners in an eternal dance. The violent, messy death of a star gives birth to an object of incredible precision, and that very precision is then modulated by the subtle, enduring scars of its creation. The universe, it seems, does not deal in absolutes. It operates in the beautiful, complex space between perfect symmetry and generative asymmetry. What does this tell us about our own place in the cosmos? We are biological beings living in a world of constant flux, of growth and decay, and we too are built from imperfections that make us uniquely functional. Our quest to understand a pulsar's wobble is, in a way, a quest to understand a deeper truth about existence. The value of this knowledge is not measured solely in the technologies it might one day inspire, like a galactic positioning system. Its true worth is intrinsic. It is the value of looking at a flickering point of light in the vast darkness and understanding not just what it is, but what its subtle rhythms mean for the fundamental rules that govern everything. This pursuit connects us to the cosmos in the most direct way possible, transforming us from passive observers into active participants in a grand, unfolding story of discovery. Every spinning object in the cosmos, from a child's top to our own planet, hums with this same rhythmic sway. The precession of a pulsar is not an isolated curiosity. It is a single, powerful note in a universal symphony of motion, one that connects the infinitely large to the infinitesimally small. This tiny wobble links the grand force of gravity, which governs the orbits of planets and the bending of light, to the bizarre rules of quantum mechanics that dictate how matter behaves inside an atomic nucleus. It bridges the chasm between the colossal explosion of a supernova and the future promise of a spacecraft navigating by starlight. Each measured precession is a point of convergence where astrophysics meets nuclear science and fundamental theory meets practical application. The universe reveals itself not as a collection of separate phenomena, but as a deeply interwoven system, a clockwork of unimaginable complexity. In this cosmic machine, a slight imbalance in a distant stellar corpse becomes a key that can unlock multiple doors at once, teaching us about the birth of stars, the nature of time, and the very fabric of reality. Our ability to listen to this whisper and comprehend its meaning marks a profound step in our journey, transforming us from inhabitants of a single world into conscious participants in a vast, interconnected cosmos. The humble wobble of a pulsar is a key that unlocks multiple doors across the cosmos. This subtle sway, born from a star's asymmetry, is far more than a celestial quirk. It is our most powerful probe into matter denser than an atomic nucleus, a natural laboratory for testing Einstein's theories to their absolute limits, and a potential beacon for a future galactic positioning system. This journey reveals a beautiful paradox that the greatest discoveries often spring from nature's imperfections. A perfectly smooth, symmetrical pulsar would be a silent, unreadable clock. It is the tiny mountain, the internal tug of war, the lopsided shape forged in a supernova's violence that gives the star its voice. Its rhythmic precession is a message, and we are only just learning to translate its full meaning. The story of this wobble connects the quantum world to the cosmic scale, linking the bizarre rules of quarks and superfluids to the future of human navigation among the stars. It reminds us that to understand the universe, we must sometimes listen not for the perfect, steady beat, but for the quiet, telling tremor within it. We would love to hear which part of this incredible story resonated most with you. Was it the glimpse into impossible matter, the testing of fundamental laws, or the vision of sailing by these cosmic lighthouses? Share your thoughts and join us for more journeys to the very edge of understanding.